Chapter 2 is a very important chapter, and if you look at the amount of time I've allocated for it in our schedule, you'll see we've got 4 lectures out of this single chapter, and that tells you that this is an important chapter. We're going to go through it a little slower because there's a lot of math in this chapter, and this is very foundational for a lot of things that we'll be seeing throughout the semester. So it's really important to understand Chapter 2. Chapter 2 is titled Measurements and Calculations. We're going to try to work through the first 4 sections today. In science, in general, chemistry as well, we make measurements. So we make in science we make measurements. A measurement is a quantitative description of something. It involves a number. The number is important, but the unit is also important. So a measurement has 2 parts, the number and the unit. So if we measure this block and say that it is 1 centimeter, we have the number part and the unit part. This little sliver here, 1 millimeter. We can't just say it's 1. 1 what? 1 mile? 1 millimeter? The unit is really important. The number gives us a comparison, but the unit tells us the scale. So in science, it's very important when we have measurements that we include the unit. Okay, so I want you to get in the habit all throughout the semester, always write down the unit. Yeah, it's a little tedious sometimes, but it's important. Units are really important. In science, we deal with some very large numbers and some very, very small numbers. And some of them are so large or so small that you can't enter them on the display of your calculator, because most calculators will allow you to put in about 9 digits. So if you have a number that is like Avogadro's number, which we'll learn about later, 6 times 10 to the 23rd, that's a 6 with 23 zeros after it. You can't enter that into your computer just by doing 6, 0, 0, 0, 0. You run out of spaces. So we use scientific notation to express very large and very small numbers in a more convenient manner. So we need to understand how scientific notation works. So scientific notation basically expresses a number as a product of a number between 1 and 10 and the appropriate power of 100. So if we look at this number, 1,000 million billion, this is what, 93 billion, right? So hopefully you will agree with me that 93 billion is the same as 9.3 times 10 billion. We're factoring out tens. So let's look at a maybe a smaller number. Let's look at 473. What if we factor out a 10? We divide that number by 10. 473 is equal to 47.3 times 10. That's true, right? What if we factor out another 10? It's also equal to 4.73 times 10 times 10. All we're doing is pulling out tens. 10 times 10 is 10 squared. So this is equal to 4.73 times 10 raised to the 2nd power. And just classroom note, if you have a hard time seeing the screen, feel free to move around. And I don't mind if you move during class. Can you see that screen? Not really. Feel free to move. That's absolutely fine. So this number, 93 billion, is equal to 9.3 times 10 billion. Well, 10 billion is 10 raised to the 7th power. 10 raised to a power is easy to understand because the exponent tells us how many zeros are after the 1. If we look at this number, there's 1, 2, 3, 4, 5, 6, 7 zeros. 10 to the 7th power is a 1 with 7 zeros after it. 10 to the second power is a 1 with 2 zeros after it. So what we're doing is we're just factoring out powers of 10, and we're always going to do that so that this number is between 1 and 10. You're going to have a number, and then possibly one digit, and then possibly a decimal point and any other digits. But it'll never be less than 1 or greater than 9. It'll never be 10 or greater. So we're going to do some examples of this. So we can express any number as in scientific notation. The power of 10 depends on the number of places that we move the decimal point, and the sign of that exponent depends on the direction. So we were talking about factoring out powers of 10. When we divide by 10, the decimal point moves one place. Let's see. So the power of 10 comes from the number of places the decimal point moves. The direction is whether it's positive or negative. There's probably an example coming up, but I'll just make up another one right here. So let's say 98764. I'm just making this up. So if we want to put this in scientific notation, there is no express decimal point written in this number, but if there was a decimal point, it would be at the end, right? So we need to factor out tens so that the decimal point ends up over here. So we need to move the decimal point over there. We need to see how many places we're going to move it. We're going to move it 1, 2, 3, 4 places. So this is going to equal 9.8764 times 10 raised to a power. The power is going to be 4. How do we remember whether to make that a positive 4 or a negative 4? Well, it has to do with which direction the decimal point moves. There's a lot of things where we have a correlation between, here we've got moving the decimal to the right, moving the decimal to the left. And that correlates with positive exponent, negative exponent. So you kind of have a 50-50% chance of guessing correctly. Well, that's not very good. It helps to have some little clue to help you remember. It's real hard to just associate two pairs of things and get them right all the time. So the way I think of this is I look at this original number. 98,000, is that a big number or a small number? How do you feel about a big paycheck? You feel positive or negative? Positive. So if this is a big number, the exponent's positive. 10 to the 4th is a 1 with 4 zeros after it, right? 10,000. And you can try this on your calculators. You should bring your calculator to class every day. There will be weeks where we may not use them, but bring it anyway and pull it out right away and use it whenever you can. So try that on your calculator. Take 9.8764 and multiply by 10,000. You should get our original number back, 98,764. These numbers are exactly the same value. They look different, but it's just a different way of writing it out. What if we have 0.017? And we're going to put that into scientific notation. Well, we need to make this decimal part, this first part of scientific notation, this number has to be between 1 and 10. So we're going to have to move this decimal point to after the 1. We're going to want this to be 1.7 times 10 to the something. So we're going to, it's second, we're going to move it 2 places. And then we ask ourselves, positive or negative exponent? Is that a large number or a small number? It's a small number. How do you feel about a small paycheck? You feel negative about that, right? This is a negative exponent. So just a little bit about what does a negative exponent mean. 10 to the second power is 100, a 1 with 2 zeros. It's 10 times 10. 10 to the third power is 10 times 10 times 10. 10 times itself 3 times. That's what exponents are. If we make that a negative, 10 to the minus 2, a negative exponent means that it's 1 over 10 squared, or 1 over 100. It means we're dividing by 100 instead of multiplying. So that's how these small numbers have negative exponents, because we're actually multiplying by 100 to make that number look larger, and then we have this negative exponent up here. Any questions yet? We're going to do some more examples. So I jumped ahead a little bit, but here's the written out description. If we move the decimal point to the left, yes, sorry, I just had I don't know what kind of a moment. If we move the decimal point to the left, the power of 10 is positive. That's how your book explains it. And like I mentioned, left, positive, right, negative, that's hard to remember. So in brackets there's my method. If the number is large, the exponent is positive. Here we see 345. The decimal point originally would be after the 5. We need to move it 2 places for it to be 3.45. In scientific notation, there's always one non-zero digit, the decimal point, and any other numbers that may be there. You'll never have 34.5. So the exponent's 2, and it's plus 2 because this is a big number. If the decimal point is moved to the right, or better, if the original number is small, then the power of 10 is negative. So here, 0.0671, we're moving the decimal point 2 places again, so it's after the 6, 6.71. The exponent is 2, but it's negative because this is a small number. So, concept check. Which of the following correctly expresses 7,882 in scientific notation? And so, I'm going to try to teach you some test-taking strategies too. I will be giving you multiple choice exams. So this is a multiple choice question. One approach to multiple choice questions is first look at the answers and see if there are any that are obviously wrong. Are any of these obviously wrong? B. What's wrong with B? The decimal point's in the wrong place. It needs to be after the 7. So we can just knock B out of the running right away. That's not right. Is there another one that you can see that can't be correct? Without a A? D. D is the other one that's obviously wrong, that you don't really have to do the problem, because that negative exponent means that the number is a small number, right? 7,000 is a large number. So the sign on the exponent's wrong. That one's wrong. Okay, so now let's actually do this and see. So it should be 7.882 times 10 to the something. And the decimal point was here. We move it, 1, 2, 3 places. So the answer must be C. Any questions? So that's one strategy for answering multiple choice questions. First, knock out the ones that are obviously wrong. Sometimes seeing all those choices confuses you. So another strategy is don't even look at the answers. In fact, maybe even cover them up with your calculator or scratch paper or something. Don't even look at them. And just do the problem. And then look and see, does my answer match up with one of those? That's a different approach. Here's another one. Which of the following correctly expresses 0.0000496 in scientific notation? So how many places are we moving the decimal point? It's here, 1, 2, 3, 4, 5. So the exponent must be 5, right? So we can say, well, there's only one with an exponent of 5. Must be that one. And then let's just check. Okay, it's a negative 5, and that's correct because this is a small number, it's less than 1. And the decimal point's in the right place, it's 4.96, not 496 like it is at the bottom. Any questions? More examples. Let's express these in scientific notation. So you try to do this on your notes. I'll give you a minute. For the 12,500, do that one first. Does anybody have an answer?
1.25
1.25
times 10 to the 4th.
times 10 to the 4th. Yep, so the decimal point was here, 1, 2, 3, 4. The exponent's 4. 12,000 is a large number. It's a positive exponent. Anybody curious why I didn't write the zeros down? We don't need to. We will learn later in this chapter what to do about those zeros. For now, when you have zeros at the end, just leave them off. How about 247? What's that in scientific notation? 2.47 times 10 to the 2. The decimal point was after the 7. We need to move it 2 places. You may feel silly drawing those little curvy things, but it really does help, And nobody's going to look at your paper and say, oh, he drew little curvy things. It's better than getting the answer wrong. 2 places, 247 is larger than 1. It's a big number, positive exponent. How about 10? 1 times 10. Okay, but we have to have an exponent. 10 to the 1. Okay, so the number like 10, we wouldn't necessarily put that in scientific notation, but we can put it in scientific notation. And just for fun, how about the number 2? What would that be in scientific notation? 2 times 10 to the 0. Because if we go 2 times 10 to the 1, that would be 20, right? 2 times 10. Anything raised to the power of 0 is 1. And that fits in the number of zeros. So 2 is 2 times 1, right? 10 to the 0 is equal to 1. It's a 1 with 0 zeros after it. So that was an extra one. How about 3,500,000? 3.5 times 10 to the 6. So we move the decimal point over 6 places, put it after the 3, and then it's going to be a positive exponent. How about 1430? 1.43 times 10 to the 3rd. So here we're getting into some meat now. Monday was kind of fluffy stuff. This is real stuff, okay? What's really important is that you understand this as we go along, okay? And this is a very beginning class in chemistry, okay? And so I'm assuming that most of you have not heard this stuff before, and that, I can explain it a couple times and it's still probably not super clear. If you're not understanding what we're doing here, you should ask questions. If you have a question, if you're not getting it, I'd be willing to bet there's probably at least 5 other students that aren't understanding it either, and they'll be so grateful to you for asking a question, okay? So think about, why are you in school in the first place? Is it for fun? No, it's because you want to get somewhere, right? You need this class before you can take the next chemistry class before they'll let you into nursing school or whatever. So keep your eyes on that goal that you have. You're here for a reason. So in here, we're not here to impress each other or to look cool to each other. We're here to learn. And so just focus on learning. And if you're not getting it in class, ask right away. It's not going to get better. It's not going to go away. Okay, this stuff will come back and get us over and over again. So it's really important, understand as you go along. Yes?
Then why can't you write, let's say, 0.125 times 10 to the 5th?
Good
Why
question.
would it be only from 1 to 10?
So the question is, why can't you write 0.125 times 10 to the 5th? Very good question. Why does it have to be 1.25? Because that's how everybody decided to do it. It's just a general rule. So that the number in front of the time sign, there's always a digit, a non-zero digit, and then a decimal point. Always. Just pattern. No specifically great reason, but just, I think the best reason is we all decided to do it that way. And so it's a little bit, did I talk to you guys about the dollar biller on Monday? No? Okay, so it's a little like baby talk. So when my son, who's now a freshman at UC Santa Cruz, when he was about 3, we were at a restaurant and he kept talking about the dollar biller. I'm like, what on earth? It took us a little while to figure out what he was talking about. He was talking about the cash register. It was the dollar biller. Okay, so we figured out what he meant, but that's not how we say it. Why do we call it the cash register? Because that's its name, right? So there's a lot of things in life that there's not really a reason that we have to do it that way. And would I understand what you meant if you put 0.125? Yeah, I would understand. If you use it in a calculation, could you get the right answer? Absolutely. Just by convention. And so in a question where it's saying, express this number in scientific notation, then if you do 0.125 times 10 to the 5th, the answer would be wrong. If, on a lab, you're writing out your answer and you wrote it out like that, I would say, well, it's better to write it this way, but I would count it correct because I know what you mean. Good question. Anybody else have a question? I think we've got more examples here because those were all positive exponents. So here's some more examples. Let's express these in scientific notation. So, 0.135, what's that? Anybody?
1.35 times 10 to the negative 1.
1.35 times 10 to the negative 1. Very good. So we need to move the decimal point so it's after the 1. That's moving it one place. So that's why the exponent is 1. The exponent is negative because that's a small number. It's less than 1. How about 0.0024?
2.4 times 10 to the negative 3.
2.4 times 10 to the negative 3. Right. Sometimes the decimal point, if you're writing with a pencil or even the stylus does it, it ends up being too tiny to see. I guess that's another advantage of writing the decimal portion the same all the time, because we know that the decimal point will be after the first digit, so you can look for it. So that decimal point gets moved 1, 2, 3 places. It's a small number, so it's negative 3. How about 0.104?
1.04 times 10 to the negative 1.
1.04 times 10 to the negative 1. Love you guys volunteering answers. And different people, that's excellent. So we move it over one place, and it's a small number, so the exponent is negative. If the left, right, positive, negative thing works for you as described in the book, go ahead and do that. This is what works for me, and it seems to work for more students. How about this next one? It's going to be 3.06 times 10 to the what? Negative 2. Now this guy, I don't know about you, but when I look at that many zeros, I have to point and count them. 1, 2, 3, 4, 5, 6. So 6 zeros. I'm going to have to move it over here. That's going to be to the -7. 7.2 times 10 to the -7 because I moved it 1, 2, 3, 4, 5, 6, 7. And that's where the little scallopy things. It just makes it a lot easier to count. Any questions? You should learn how to go back and forth between decimal and scientific notation, just using your brain. On your calculator, though, there are a lot of calculators that have a function that allow you to express the number either way. The TI-30XA is one of them. And so you can look around at your calculator. If it has buttons that say FLO, SCI, ENG. With some calculators, this is hidden in a menu. Some of them just have it straight out as a second function, like the TI-30XA. FLO will give it to you with a floating decimal point. That means the decimal point could be anywhere. That's the regular decimal notation. SCI will put that number in scientific notation. Is it cheating to use that? No. No, it isn't. I would encourage you not to rely on that completely, though. Do it in your head first and use that to check your work. So if you want me to look at your calculator later, I can do that for you.